I'm happy to be here actually on a combined AI and IoT forum. I spent all my life in software more or less. First 10 years in telecom platforms, and then we built our own startup with an app platform. I've been in e-commerce, but always in digital. So delivering to financial customers, media customer, travel. Now I'm within Dynniq. Dynniq is an international organization, 3,000 people in smart mobility, smart energy and smart parking. We're talking about connected assets. And I want to give you a few examples and use cases of the use of IoT and AI in smart mobility mainly. And Steven will take over as we have hired GoDataDriven to help us in our capability build-up of data science, data analytics. And Steven will show you what he has encountered organizationally and technically within our organizations. But first, a few use cases. We are, as I said, in smart mobility, and there's a lot of going on over there. We are in a world where we see connected and autonomous driving. That means that cars get more and more connected to each other and also to the infrastructure. I'll show you examples of that later. And also city governments and also national governments are thinking about the future with these cars in it. We have electrification of cars. We have a policy within the cities that they want to more or less make it cleaner for the citizens to live in. So the cars should go more out of the city. It should be more friendly for bicyclists. So there's a lot going on in mobility. It's more or less a modal shift, and the flow of cars and vehicles, also trucks, within the cities is looked into to improve flow. And that's actually also the mission of Dynniq, to facilitate that people and goods arrive at destination in a more safe, efficient and environmental friendly way. You see in this picture also some IoT innovations. So for example, traffic poles, we have I think 30% of all the traffic lights in the Netherlands installed by Dynniq, and you now see that there are sockets in the lamps that you can use for IoT things, like to measure things, to measure movements, to measure these kind of things. You see some energy. In the energy field, we're talking about microgrids to charge electronic vehicles, because the grid, the electricity grid, is not capable of charging those vehicles. It's just too much, you know. So what needs to be done is local solar cells, for example, again, and using AI to manage that local network. I take you a little bit through the history of how this new world of mobility has come about, because actually the automotive industry has talked about this also for 10 years already, and also made standards for communication between vehicles and between vehicles and infrastructure. This is our research roadmap, but also history. It started with some of the projects above. And basically there was a reference architecture designed by the European standardization bodies, ETSI and Artico, where we're a member of. And you see here kind of a picture, I don't know if it's clear enough, which basically shows that the vehicles can talk to each other, and the vehicles can talk to the infrastructure via either connected communications, which goes via cellular, via the cloud, via 4G for example, but also we call it Wi-Fi P, so Wi-Fi P. It's a short-range communication protocol designed by the automotive industry to, for example, give the braking indication to the car behind, right? So for safety. And that same protocol can be used for the infrastructure to guide vehicles off the road. The projects below, these are the things that are actually happening. So we're now rolling out this infrastructure with roadside units that can talk to the cars. The car information is shared with the cloud, and in the cloud obviously AI can do a lot of massive calculations. Examples there are if the wheel is spinning of a car, it can be given to a roadside unit which gets into the cloud, and the next car the wheels also spinning, you can be pretty sure it's slippery on the road. That same message, slippery on the road, can be given back to the roadside units to the next cars arriving or kilometers ahead, for example. So that is a new way of indicating that something is wrong to, have a safer road. There's also, you have some really new projects around cycling, transit. This is around automated vehicles that drive on the road and the driver is actually sleeping, which is possible in level 4 self-driving cars. But now it has to get off the road into the city, and it can't do that by itself, so it has to wake the driver up. The driver doesn't wake up, so what do? This is what Translate is trying to do. With roadside units, it guides the car to a parking lot next to the ramp, right? And until the driver is awake again and drives into the city. These are the things that's really now in research phase, coming at us in the next 5 years in the hybrid phase of autonomous cars and normal vehicles. And I want to show you a short movie just to still get an impression of this world about Maven. Maven is, like you see, managing automated vehicles in an urban environment.
Think of the complex urban environment that consists of intersections and mixed traffic. Think of a future where automated vehicles will be part of this environment. As a member of research project Maven, Dynniq is coming up with traffic management solutions for these automated vehicles. One of these solutions is GLOSA, a technology that gives an optimal speed advice so you don't have to stop at the next traffic light. This improves the flow of the entire traffic network, handling traffic in a more efficient and environmentally friendly way. Imagine you are driving the green car and it is equipped with the GLOSA speed advice. Notice how you don't have to stop for the red light. Maven uses GLOSA, but it goes beyond just giving speed advice. Maven works as the brain of a network that also contains automated vehicles. For this intersection, Maven knows most vehicles, including the cyclists, go straight on, so it gives them a green light. When the green automated car sends information to Maven, communicating its intention to turn right, Maven quickly analyzes and safely switches the cyclist's light to red and the right turn to green. Then Maven sends speed advice to the automated car, allowing it to pass the intersection without stopping. Maven also helps automated vehicles choose the lane with the shortest queue. It is an immediate decision for a human driver, but for automated vehicles, this is not yet possible. Maven monitors the vehicles in every lane and selects the lane with the shortest queue. It informs the automated vehicle to use that lane. These Maven solutions are not only simulated, but will also be tested on real intersections in Helmond, the Netherlands. In the future, this technology with automated vehicles has the potential to eliminate stopping at intersections completely. An average vehicle emits 27 grams of CO2 to stop and re-accelerate. For an intersection where 10,000 vehicles pass per day, there is a potential saving of 80 tons of CO2 per year. Together with Dynniq and our other partners, Maven prepares your world for the future.
Let's see how far we come. So like I said, Dynniq, a company of connected assets. That's the beauty of it. For the ones who don't know, Dynniq has a history within Imtech Infra and peak traffic, which were in a lot of markets that I just explained in more or less the assets that are on the roads. So those are the traffic lights, those are the matrix signs above the roads, tunnel, bridge, and sluices infrastructure, technical automation more or less around the road. And now the interesting thing is that because these are now sensor-based and can communicate with the cloud, all that data is now coming available. So as Dynniq, we've been building on our architecture, flow sense service architecture, to not only sell to our customers the products you see here on the below, the lights and the signs you see in the parking garages, for example, the beams, the video cameras, in energy, the batteries, and the roadside units that you just saw. Those are all assets that we sold as products, but more and more it will be a service based on the cloud, and that IoT data is more or less managed in that cloud. So that will be real-time data, historical data, all combined with the applications that you see on the left. We of course had already a lot of applications, but those are more or less siloed. So we started an initiative to make that more uniform, also to make the data lakes more uniform and the way we model it, so that we can really use the assets together, get external sources in and APIs to disclose that information. And the interesting part here for this conference, obviously, next to the IoT is the AI part. This is what we really add, because previously the traffic lights, and still some are completely not connected. That might be a surprise to you, but those are completely independent of everything else. And that is now changing, because in the Netherlands we had a talking traffic project that connects these traffic lights to the cloud for all traffic controllers. So now there's a possibility, Dynniq provides also that possibility, for example, to trucks to ask priority in front of a traffic light. Also for cyclists, with an app in the pocket you can now drive, and the traffic light knows that you're there and drives through. So those things are possible now, adding the data analytics and presentation layer. Some use cases before I hand over to Steven to explain more on what we did on a specific project is also the control systems that you'll see, the bridges, tunnels, sluices, big things. Previously had technical automation. What you now see is that there is very small sensors making a lot of difference. For example, for the sluices, we can now, by just placing a video camera, we can detect if a large cargo ship goes too close to the door, so that it could harm the door, right? So, and then gets an alarm. We can put sensors for the doors itself to measure electricity and see if the doors are not jammed somehow. Same with bridges. You can measure on the electricity. You can see when you have to do maintenance on those bridges. So there's a lot of assets that we can now monitor to make it more safe and efficient to operate. And there's just another example that I wanted to mention. That is, we're getting more and more in a virtual world. So next to the assets I mentioned, we also had emission monitors. Cities are interested in the emission around and in the cities. And one of the applications that we have in a research project have developed in the UK actually is to have a virtual emission monitor. It looks at speed, flow and the fleet characteristics along highways or other roads. When you know what kind of cars are driving, what velocity and what the flow is of those cars, you can measure virtually what kind of NO2 emission there is. And that seems to be pretty accurate. So this is the data that we've used in this case. And what you can see that it is pretty close, when you model that as an AI model, pretty close to the real measurements that you would do with physical hardware. And of course physical hardware is much more expensive to install. It's it's out there, you have to do it. This is all done by software, which makes a whole lot of measures now possible. Just virtually monitor it, and when it's getting too high you can take measures. So that's a short overview of what we do in smart mobility, and I wanted to give the floor to Steven, who has been working on one of our most interesting projects to more or less make from a product go to more a service. So instead of traffic controllers, we go to flow as a service. And we hired GoDataDriven, like I said, to help us get our own, within Dynniq, our own capability of data engineering and data science. And GoDataDriven helps us more or less to get there, to get us up to speed in that aspect. So Steven, the floor is yours.
Thanks, Peter. Can I have this thing? So I'm going to tell you a little bit more about how we help Dynniq to become more data-driven. So I'm helping Dynniq to set up a data lab, so like innovation lab where we work on data products. So there's two things in this data lab that we do. The first thing is that we build a solid foundation for data engineering. So think about a technical platform and coaching. And we bring in two seniors to help Dynniq grow and get the capabilities to do it themselves. And the second thing is that we do a lot of rapid experimentation of all kinds of use cases and products to see if there's any value in the ideas that are out there in the business. So it's those two things that I want to talk about a little bit more. First, the foundation. So how do you build up a data science capability or a team? Like if you don't have that much yet. Then the thing we do is we start with a core team. So in this case, GoDataDriven comes with a lead data scientist and a lead data engineer. You can't start without seniors. You need people to lay out the best practices and to tell you how you have to set up your code and your technology. And then Dynniq provides a business liaison, somebody who's going to get out there in the business, collect use cases, prioritize use cases, talk to the business, and find out which cases to work on. Then with this core team, we built a data platform and we start working on the first use case. And as soon as we grow a use case and the use case gets mature, then we start creating data teams, more like that they are going to focus on one product specifically and continue to develop their product more and more. So there might become a business analyst in the team, there might become a product owner in the team, and there will also become or junior data scientists or junior data engineers will also join the team. And the role of the senior data scientists and the senior engineers, so my role, instead of developing the prototypes myself, will be more like coaching, right? So with each new prototype we do and that we bring to production, I will coach more and more of the juniors joining the team. So that's how we scale out a data science capability within an organization, but you start with those three people. So if you have those use cases, we collect them, you have to score them on viability and on business value. And yeah, you go through a kind of process, right? So this is what the business liaison does with the lead data scientist, and we start collecting IDs. Then we prioritize the board. Peter chooses which ideas have actual value, and we're gonna look into next. And then we start proof concepting, and after we've done a pilot and it has proof of value, then we're gonna hand over to the organization who's gonna do more of the operations and who's gonna maintain the product into the future. And we start grabbing a new use case. So to do all that, we need to hire people, and that's also what the lead data scientist, the lead data engineer do. They start recruiting people. So we need to make job descriptions. We're looking for people here who want to work there. We are going to do all kinds of things to get a data science capability growing. So that's about growing a team. So that's one of the tracks we do, and then the other track is to build a dashboard or to build the first pilot. And the first pilot that was selected was to create a flow as a service. And the way we do products, the way we develop ideas within GoDataDriven is not by taking years to build a data foundation, then taking another year to build the pipelines and do the ETL, then doing the modeling, taking another half a year, etc. And but we're trying to slice the whole pyramid at once for each product. So specifically for the use case that we are looking into, we're gonna see, okay, which data do we need? We're gonna get that. We're gonna try to do all this in just a month or a 2-week sprint, even if it's possible, or maybe 2 months if it turns out that there's more complications than we thought. But we try to get there as soon as possible. So the use case I want to talk you through, which we have done over the last month, is flow as a service. So Peter already told you that traffic is becoming more intelligent. So one thing you want to do is measure how good the performance is of an intersection. So let's say this is a city, and you might recognize which city it is if you live there. but there's a couple of intersections which are called together a network of intersections, and you want that network to be optimized perfectly, right? So you need to know, okay, what's the delay at specific intersections? Is there red light negations? What's the wait time at specific intersections, and how is the network performing? So we need to get insight into that, and we want to make it fully scalable. So we need to get some dashboards like these, but we want, after we've done it for this pilot city, we want to do it for all cities internationally. So we need to think about how this product can grow. And well, growing these days, you do with the cloud, right? So you don't do your own hardware anymore. You don't do your own cluster management, but you go serverless. So we had two options in this case that we considered. Microsoft and Google. It might be interesting to talk to you a little bit about through what choice we made for this case. So Dynniq already has a lot of cloud things going on, but we needed to make a choice to be more uniform and to choose one platform and grow everything in there. And you don't want to have a data lake in different platforms. So we helped advise them on which platform to choose. So Dynniq was already using a little bit of Azure. Azure felt a little bit more of a safe option for the clients of Dynniq to store the data than a marketing company like Google. So that was an argument that was very heavily weighted in the decision. But Azure, Microsoft, doesn't offer a good Spark service, which is completely blacked out because of this line I see. But Spark is software we use, right, for big data. So that it's the service they offer themselves. You have to do a lot of cluster management, which requires a lot of data engineering, which is a hard skill to attract. So you want to start with a serverless Spark offering. So Google has all that, and is a bit more on the a bit more advanced on the serverless offering. So you don't need the engineers yourself, but you can just click and say, okay, I need 3 machines to get going on. But luckily in Azure, eventually we've chosen that because Azure has a Databricks option, which is a managed Spark service. So as a data scientist, you can just say, I need a cluster with 5 cores, 10 RAM gigabytes, whatever, 3 machines, and I'll just get it in an instant, and there's no engineer involved in that process. So that makes it very easy to start doing data science on a big scale with just a service like that. So after you've chosen which cloud provider, you've got to get to work. So what kind of data do we have? So the traffic roadside units that Peter talked about look like this. You might have noticed them outside of the way. If you have never, you will notice now. And also, those things, what they send out is like bytes, like raw bytes, right? So it's a very hardcore data, and you can't do anything on it right away, so you need to translate. So the first part was about making sense of it, and the 2 major data sets that we are looking into is to try to get a sense of the sensors, which are the induction loops in the frames in the road, and you will see it looks like this, right? Eventually, if you translate it, it says on this timestamp it was occupied, then it was not occupied, then it was occupied, then it was not occupied, right? So if someone's stopping in front of a traffic light, then it's occupied. A bit later, it's not anymore. On the other hand, we have the signal status. So it's like this. So was it green? Was it green? Was it amber? Was it red? Was it green? Was it amber? Was it red? So both of those things are pretty crucial, and you can do a pretty cool analysis on those. So just looking at the detectors, for example, you will see a pattern like this, and the line is the amount of traffic volume on the specific detectors per day. And you'll see there's a clear weekly pattern, right? So on average, you would expect this amount of volume, this amount of cars on the road. But in the weekends, the grayed out sections, there's a lot less traffic on the road. And then you see distortions in the pattern, right? So on this Monday, apparently a lot less people were driving on the road. Why? Second Easter day, right? So another thing, King's Day, a lot less people drive. And Hemelvaart, a lot less people drive. So this is the first insights you get from the data, and already gives you some value. But now we're just looking at the detectors on itself. So you need to combine detectors and signal groups, and that's when you can do interesting stuff. And within the traffic industry, I didn't know about this a month ago before, also. But there's like intersection topologies, which is just a combination that tells you, okay, which detectors, like which sensors belong to which lane, like a road, and then here it will tell you also of this detector which sensor signal group it belongs to, right? So eventually you can look into all the maps, and then you can make sense of which detectors belong to which signal groups. And then if you know that, then you can do cool stuff. For example, you can count how many people drive through red, right? So if it's red and someone drives through the induction loop and then goes away again instead of waiting until it's green again, you know this guy was driving through red. Right, so it's nice. So now we can make sense of stuff happening on the junction or an intersection. So this is cool. It's getting more interesting now. And even more interesting, we can do like queue modeling and queue theory, right? So we can count how many vehicles are getting into the queue, how many are leaving, how many are dying, and birth. It can happen, birth and death, because there might be a gas station here, right? Or people switching lanes because they thought they would go straight, but then they decide to go right. Happens. So you can do all these kinds of analysis, and it gets even more interesting. And then you eventually get to the point that you have those KPIs and you can measure the performance of your junction. So you want to do something more because you want to alert the servicing people of the intersection, or you want to alert Dynniq as a service contract with the municipality when it's going wrong. And then you can do like anomaly detection over time. So you expect it's going to be within the red boundaries, and as soon as the KPI that you're measuring is exceeding those boundaries, so there's something, then it's not doing normal behavior, right? So we know that with 90% confidence, it's gonna be within that, and in this case, within a very short interval, we had like a lot of anomalies. So let's look into that with the people maintaining the road and see if there's something going wrong at that moment. And in the future, you want this in your dashboard, and you want an alert to be sent out if this stuff happens. So for that you build a dashboard, and Azure has Power BI, so we can build a dashboard like this. So this dashboard you'll see again the city, and you can visualize things like the percentage of green time over time. You can look into specific counts, or you can show the number of red light engagements in this period. You can give the business a lot of insight in what's going on, and we can show the anomalies here that's happening. So yeah, all that happened in Azure. So what we've been doing, well, I was talking you through all of this. We had the original data coming out of the traffic light controller. It was used to be, it is sent to a database Dynniq maintains, but we're extracting it every 5 minutes. We're putting into it Azure Blob. We're then loading it into Databricks, where we do all the machine learning and the anomaly detection and all the KPI development. Then we're storing it in a SQL database so that we can visualize it really quick with Power BI. So that's the whole chain to be done. And we try to do it cloud agnostic, right? So we use Python, Spark, Airflow, which are all open source tools, meaning that if we want to switch to Google Cloud later, we can, because all the code is just can just be used on any other platform. So we try to avoid vendor lock-ins in that way. So I think that's important. I think you agree, hearing like this. So coming back to Peter's FlowSense architecture, yeah, all of these things is something we want to do. We want to make Dynniq more service-driven, more data-driven. So there's a long-term vision. But to get there, we're just slicing through it, product by product, and try to create the whole value chain, product by product, and start creating value before we invest like years in putting this and another year in that and another year in that, and then it becomes a major IT project which is going to fail. So that's the way we approach it, and that's the end of my story. So Dynniq and I, we are both hiring for this specific team and for to come join us in this data engineering and data science. So if you're also annoyed and fed up with waiting for red lights when you're driving your car, then you can do something about it and come join us.